All right, so we're going to continue on further into Chapter 11. This is Section 11.4. This is on properties of logarithms. So what I'd like to do is, first of all, let's go back to this handout here, and let's look at some of these properties, and then I'm going to see if I can tie them together with the rules of exponents, because as I said before, logarithms are exponents in disguise. So for instance, like this very first one here where it says the log base a of 1 is 0. So I think we had some things that look like that earlier. So if I said, the log base 8 of 1 is 0, because we know that 8 to the 0 power is going to be 1. I think that one's pretty straightforward. All right. This one here, the log base a of a. So what power would you have to raise a in order to get a? So for example, if I had, say, the log base 6 of 6, you want to ask yourself 6 to what power would give you 6? That would have to be 1, because we know that 6 to the first power is just 6. Now, the rules that are probably the most important and the ones that we're going to use the most are rules 5 and 6 and 7. All right. So let me go to my lined paper for just a moment here, and let's just kind of refresh ourselves on rules of exponents, because as I said, logarithms are exponents in disguise. So for example, if you think back a little bit in your algebra career, if you had, say, x to the third power times x to the fifth power, hopefully you remember that these two exponents need to be added. This would give you x to the eighth. So if I had, say, let's say for y cubed times, say, y to the fourth power, again we're going to add those exponents. Oops. Let's make that a 4, so that I would have y to the seventh. So if we're multiplying things of the same base, we end up adding the exponents. Okay? All right, likewise, just to remember our rules of exponents, if I had, say, y cubed, and I wanted to raise this to the fifth power, so something with a power, we're raising it to another power. Remember, these exponents need to be multiplied. So if I had, say, 2 cubed, and if I was squaring that, this would give me 2 to the sixth power, which is 64. And lastly, the other rule of exponents we need to kind of remember is if I had, say, z to the sixth power over z squared, remember we need to subtract the exponents. It's always 1 on top minus 1 from the denominator. So this would give us z to the fourth. Or let's say, for instance, if I had something like, w squared over w to the negative 5 power, I'd have w to the 2 minus negative 5, or w to the seventh. But we have to keep in mind those rules of exponents. So let's go back to our handout here. Now you're saying, well, how does this kind of fit together? So here I'm looking at a product. I'm multiplying. If that's the case, then I need to add the logarithms. Just like over here, when we were multiplying things of the same base, we added the exponents. Same idea. This one here, I know my superscript is very tiny here, but here what I've got is I have log base a of m to the r power. This is a power. We're going to bring it out in front of the logarithm. So it's going to come right out here, so that these are going to be multiplying. Just like the rule if you have something with a power, this is analogous to this rule here where you'd end up, say, y to the 12th. And lastly, if you are taking logarithm of a product, it is going to be the difference in the logarithm. So the logarithm of the expression on top minus the 1 from the denominator. Now, the other thing about these rules is they work both directions, left to right, right to left. So with that in mind, let's look at the back side of our handout here. And let's say, for instance, if we were going to write this as a sum or difference of logs. So here where I have this quotient, I could write this as the log base 3 of 2 minus the log base 3 of 7. That's it. That's all we have to do. Alright, if we look at the one that's next to it, this is going to be the log base 4 of 3p minus the log base 4 of y. Now, the only thing is that this here is a product. I'm multiplying. And when you have a product, we're going to write that as a sum of logarithms. So this would be the log base 4 of 3 plus the log base 4 of p and minus the log base 4 of y. All right. Now let's see here. This problem number 3 here. Again, we have a product. We're multiplying here. So first of all, I'm going to write this as the log base 2 of x to the 4th plus the log base 2 of y squared. Now, these things have exponents on them. We are going to take this and shift that out in front so that I would have 4 times, let me fix that, the log base 2 of x plus 2 times the log base 2 of y. We're not solving an equation, we're just kind of expanding these log expressions here. Okay, now this last one over here, I always like things where we have to put two things together, and that is, remember, if you are taking the square root of something, you are raising it to the 1/2 power. So the first thing I'm going to do is I'm going to shift this guy out in front of everybody. So I'm going to have 1/2, let's put a square bracket, let's split up this thing here because I have a product. So this is the log base 3 of 9 plus the log base 3 of x cubed plus the log base 3 of y. Now the other thing I need to do is this has an exponent. I'm going to shift that out in front. And the other thing I'm going to do here is, let's ask ourselves, what power would you have to raise 3 in order to get 9? And that is going to be 2. Alright, and now it's completely expanded. Okay, so let's try a few more of those. Alright, so let me go back to my blank paper here. And what we want to do is we're going to take these here and we want to write as a sum or difference of logs. Okay, so let's see here. I'm looking at my possibilities here. Let's say if I had something like the log base 3 of x times x plus 6 over y cubed. Alright, so you heard me say the word times. So I've got a multiplication going on here. So I'm going to have the log of, I'm going to do this in a couple of steps. Log base 3 of x times x plus 6 minus the log of what's in the denominator. Alright, but as I said, I did say the word times. The other thing is I've got an exponent here that needs to come out in front. So I would have the log base 3 of x plus the log base 3 of x plus 6 minus the log base 3 of y cubed. Oh my goodness, let me move that exponent. I said it and I didn't do it. Shame on me. So let's put that right there. Okay. Alright, so let's try a couple more here. So let's say, for example, if I had something like the log base 2 of y to the 3rd power over y plus 3 and times z. So I've got a division here, so I need to write this as a difference of logarithms. Now, a couple things here where we need to be a little bit careful. First of all, there's an exponent. I am going to move it out in front this time. I'm not going to forget. But we are dividing by everything here. But there's a multiplication going on inside that denominator. So do yourself a big favor. Minus. Let's put the square bracket. Let's write this as the log base 2 of y plus 3 and plus the log base 2 of z. So everything from the denominator needs to be subtracted. And if I put this negative sign out in front, then I'm good. Everything's fine. Okay. So let's see, let's do one more like that where we're going to expand this out. So let's say, for instance, if I had, say, the log of the square root of 15 x squared y cubed. So first of all, if you were looking at this problem here, notice there's no base indicated here, so we need to know that's a base 10 log. All right. Secondly, we know that if we are taking the square root of something, we are raising that to the 1/2 power. So let me pull that exponent out in front of the whole thing, and then we'll start splitting this up. So I'm going to have 1/2 the log of 15 plus the log of x squared and plus the log of y cubed. And lastly, let's move those exponents out in front. So I would have 1/2 log of 15 plus 2 log x plus 3 log y. All right. Now, one more here. So let's say, for instance, if I had the natural log of x plus 3 times x to the 5th power. I said times. Now this is a natural log. The rules are the same regardless what type of logarithm you're dealing with. So if I split this up, this is going to be the natural log of x plus 3 plus the natural log of x to the 5th power. So the only thing I need to do is, let's shift this in front. So I would have the natural log of x plus 3 plus 5 times the natural log of x. Now, these properties of logarithms, as I said, they go both directions, right to left to right. So let's go back to our handout for just a moment here. And I'm on the back side here. Now here we want to take this and write it as a single log term. Now I'll be perfectly honest with you, this is the direction we usually go. We're usually trying to combine something as a single log term. So in these problems here, if you have a number out in front, that's your exponent, reattach. So first of all, I would write this as the log of x cubed plus the log of z squared. Now here you got to remember your rules of logarithms, and that is if you are adding the logs, these expressions are being multiplied. So when I go to write this in a single logarithmic term, I'm going to have x cubed times z squared. And again, if you're looking at this, what's going to be the base on it? It's a base 10. Okay? All right, so let's see again. If we look at the one that is next to it here, I have an exponent there, I have an exponent there. So I'm going to reattach those exponents so that I would have the log base 2 of x plus the log base 2 of y cubed minus the log base 2 of z cubed. So if you're adding logs, those things are being multiplied, but if you're subtracting the logarithm like you're down here, you're going to be dividing by that. So as a single log term, I'm going to have the log base 2 of x times y cubed over z cubed. There it is as a single log term. All right, so let's just look at the one that's underneath this real quick here, because that looks pretty easy. Now again, natural logs, they behave the same way. So I have this exponent of 1/2. Here I have this exponent of 3. So I could write this as the natural log, instead of x to the 1/2, what if I wrote it as the square root of x plus the natural log of y cubed? Well, that color really does not show up well. So if I write this as a single logarithmic term, I'm going to have the natural log of the square root of x times y cubed. All right, we're making progress. Okay, so let's see. On this one here, I've got an exponent. Now, let's write this as, how about the log base 3 of 8 minus the log base 3 of y and minus the log base 3 of z squared. Now, when I go to write this in a single log term, anything being subtracted needs to go into the denominator. So as a single log term, this is going to be the log base 3 of, I don't have enough room is what it's going to be, so let's kind of box that off. It's going to be the log base 3 of the 8 is on top, and the denominator I have y times z squared. All right, so let's try a couple more that are like that, where I have a little bit more room to work. So let's see if our instructions here are we want to rewrite these as a single logarithmic term. Sorry, I had to pause there. I thought I was going to sneeze. Okay, so let's try a couple of problems here. So for instance, if I had, say, 4 times the log base 2 of y plus 3 times the log base 2 of y plus 6. So first of all, base has to be the same, so don't even worry about that. Base has to be the same. I've got these numbers, let's reattach them as an exponent. So I could write this as, how about the log base 2 of y to the 4th plus the log base 2 of y plus 6 cubed. Now, you got to remember, if you're adding logarithms, these two quantities are going to be multiplied. So as a single log term, this is a log base 2 of y to the 4th times y plus 6 cubed. Okay. All right, let's try a few more here. So if I had the log base 3 of y plus 2 times the log base 3 of y plus 4 minus, let's say, 5 times the log base 3 of z. Okay, so first thing we're going to do, we are going to put those exponents back on. So I'd have the log base 3 of y plus the log base 3 of y plus 4 squared minus the log base 3 of z to the 5th power. Okay, so let's see if I can squeeze it in here, single log terms. So if you're adding logarithms, they go on top. So I'm going to have y times y plus 4 squared divided by z to the 5th. Okay. All right, so let's do one more here, where we're going to rewrite this as a single log term. All right, so if I had, let's see, if I had the log, let's see, 4 times the log of x minus 3 times the log of x plus 2 and minus the log of x minus 5. Okay, now first of all, this is a common log problem because, again, look at, there's no base indicated, safe to assume it's base 10. So let's first of all reattach those exponents so that I would have something like the log of x to the 4th minus the log of x plus 2 cubed and minus the log of x minus 5. So when I'm going to write this in a single log term, anything that's being subtracted goes into the denominator. So I'm going to have the log of x to the 4th on top. On the bottom, I am going to have x plus 2 to the 3rd power times x minus 5. Okay. So the thing is, as I said, this is probably the more important direction where you're taking something that's apart and we're putting it back together. So just as kind of a sneak peek of where we're going, let me just do one problem like this. And that is, let's say for instance, if I had something like this. If I had, say, the log of log base 2 of x plus the log base 2 of x plus 7 is equal to 1. So this is a log equation. We did a couple simple ones that had a single log term in it in previous section. So what we need to do is first of all, we're going to rewrite this. This is for the next section, but I'm just giving a sneak preview here. Rewrite as single log term. So if we were to do that, we're adding logs. So I'd have the log base 2 of x times x plus 7 is equal to, and let me fix something really quick here. These are not the easiest to make up off the top of my head. Do me a big favor and make this number over here a 3. Okay, much better. I realized my mistake. Good thing I did. So now what we do is if you single log term, and it's just that the number I want on the right side there is a 3. What we're going to do now is we're going to change to exponential form and solve. Okay, so let's just do that. So that means I would have my base raised to this power. So 2 to the 3rd power is equal to x times x plus 7. Well, 2 to the 3rd power is 8. And on the other side there I have x squared plus 7x. Now, we're left with something quadratic. We'd better be able to solve this. So this is x squared plus 7x minus 8. This looks factorable to me, so we are going to get something like, I think this is an 8 and 1 combination. X plus 8, x minus 1. So we have possible solutions of either x is 1 or x is equal to negative 8. Now these are lovely looking numbers, but here's the big exception. As I said, this is kind of the next section, but I gave us a sneak preview. If we look at the original question up here, right here, so that is, if I am looking at this thing, well, both of these here, but specifically this one here, if I let x equal negative 8, is there any way that you can take 2, let's just think about this, 2 raised to a power to give you negative 8? Is that possible? I don't think so. So one of the things you have to be careful is you cannot take the logarithm of anything negative. So this answer gets tossed out. Our only solution is equal to 1. So as I said, that's kind of the next section. Okay, so the last thing that is on our properties of logarithms, and I'll be honest with you, I don't do it very often, but just so you folks have seen it, is this thing here. This is what is known as the change of base rule. And I'll be honest, I don't remember it that well because some books move the A's and the B's around. So this is where sometimes it's helpful to, helpful to use your calculator to figure something out. So let's say if we have a logarithm in one base and we can't figure it out, let's change it into another base where we can use our calculator. So looking at this formula here, A is what I'm going to call the old base, and B is going to be our new base. Okay, so let's do something that we can figure out the answer to kind of in our head. So for example, if I wanted to know what's the log base 2 of 16, so you'd say, well, what power must I raise 2 in order to get 16? That's going to be 4. We know the answer is 4. But let's say we didn't know what that was. So looking at this rule here, all right, looking at this rule and what we've got over here, my a, which is the old base, is going to be 2. That capital M is equal to the 16. So what we want to do is let's change to a base that we can work with, like for instance, something on our calculator, either a base 10 or a natural log. So let's say if we use base 10, because I know you folks like base 10 better than you do the natural log. So according to this rule here, if I had the log base 2 of 16, we know the answer is 4, but let's say we didn't. We could say this is going to be the base 10 log of 16 over the base 10 log of 2. B is the new base, so in this case here, what if I let B equal 10? So according to this, if we were to put this thing into our calculator here, just the way it's written, we should get 4. Let's see. So if I had common or base 10 log of 16, and I divide that by the base 10 log of 2, we get 4. It's exactly what we thought. All right, it's equal to 4. All right, let's do another one where maybe we don't know what the answer is. So for instance, let's say if I didn't know, or let me back up, let's do one we can figure out. Let's say if I wanted to know, well, what's the log base 3 of, I'm cheating here. I'm working backwards. Let's say log base 3 of 729. Okay, so we're saying 3 raised to some power 729. I don't know what it is. So let's figure this out by change of base. So in this case here, A, my old base is 3. The capital M is the 729. So let's say if I used natural log, something I can use my calculator with. So I would have the natural log of 729 is equal to the natural log of 3. So my B here is going to be E, because natural logs, the base is that lovely number E. You could use base 10 logs, you'd get the same thing in the end. So let's see what happens here. So if I had the natural log of 729 divided by the natural log of 3, it's 6. As I said, you could use base 10 logs as well. So if you took the base 10 or common log of 729, and then you divided that by the base 10 log of 3, in either case, you'd get 6. Because we know that 3 raised to the 6th power is 729. Now, as I said, I don't use it very often, but just so that we've kind of seen this before, change a base formula. Okay, so I think this is a good place to stop, and we'll continue on shortly.